Now we arrive at one of my favorite topics, NMR spectroscopy. By the end of today's lecture, you should be able to use NMR spectroscopy to determine the number of non-equivalent hydrogen atoms or carbon atoms. Use NMR spectroscopy to deduce molecule structures. Now this, of course, will be also done in concert with data that we can obtain from IR spectra as well. There are two different kinds of NMR we discuss in undergraduate organic chemistry. Hydrogen NMR, or H1 NMR, also sometimes called Proton NMR, and C13 NMR, or Carbon NMR. I'll begin, of course, by teaching you about hydrogen NMR. Typical hydrogen NMR spectrum looks like this. These peaks are each produced by a different kind of proton. By learning where different kinds of protons show up on an NMR spectrum and what they look like, we can deduce compounds' structures. So you may ask, Mike, what do you mean by different kinds of protons? Well, if two separate protons are in exactly the same environment, that is, they have the exact same stuff all around them in all directions, then they are the same kind of, or equivalent, protons. You should already understand this, of course, but to put your knowledge to the test, I ask you, how many different kinds of protons are there in each of the following molecules? The answer to each of those questions tells you how many different signals you'll see in the Proton NMR for those molecules. Now in Proton NMR, you'll also see that each peak has a little sigmoidal curve above it. These sigmoidal curves are called integrals. Their heights tell you the proportional number of hydrogens that each peak represents. For example, let's say that I've measured the heights of the two integrals shown here, and I found their relative heights in proportion to each other to be 1 to 3. What does this mean? Well, it means that the signal to the left could be a CH, and the signal to the right could be a CH3. But remember that these heights are proportional. In other words, I could multiply them both by 2 and get a 2 to 6 ratio. That would probably correspond to a CH2 and 2 CH3s. Or I could multiply them all by 3 and get a 3 to 9 ratio. In that scenario, this would probably represent a CH3, and the one on the right would represent 3 separate but equivalent CH3s. Got it? Now, this process of measuring the heights of the sigmoidal curves that are used to deduce structure is called integration. The sigmoidal curves themselves are also called integrals, not to be confused with integrals from your calculus classes. So are you ready to see a compound that produces this HNMR? Here it is. So you'll notice that this CH3 right here corresponds to this peak right here in pink. And these 9 hydrogens here are all equivalent. So they give one peak right here that corresponds to 9 relative to this peak's height. So at this point you should be wondering, where do different hydrogen peaks actually show up? The answer to that depends on their individual partial charges. Generally speaking, the more positively charged an individual hydrogen is, the further to the left it will appear on an HNMR spectrum. The more negatively charged, the further to the right it will appear. We say then that further to the left equals more downfield equals more de-shielded, or in other words is the same thing as saying more positively charged. And in contrast, further to the right on an NMR spectrum equals more upfield, more shielded, and hence more negatively charged. Remember that the electron cloud around a hydrogen atom is kind of like a shield. The more de-shielded the hydrogens become, the further to the left they appear on a proton NMR spectrum. These are some of the pictures of different things from movies that had electronic shields around them. If, for example, the Death Star right here were a hydrogen, then the more you removed its shield, the more positively charged it would become, and hence the further to the left or further downfield it would appear on a hydrogen NMR. Now you can see Admiral Akbar smiling here in the background. So I ask you, for each of the pairs of molecules shown here, which hydrogens do you think are more positively charged and hence will appear further to the left on a proton NMR? And why do you think that? Now, if you want to, you can pause the video here and consider the answers before going on. Most organic textbooks give lists of where different kinds of hydrogens show up on Proton NMR. I personally think those lists are usually way longer and more complicated than I would personally prefer. Here's my list. Hydrogens that are stuck to sp3 hybridized carbon atoms, single bonded CH3s, CH2s, and CHs, generally show up about 1 to 5 ppm, which are the units we see in Proton NMR, depending on what other atoms are stuck to or near the carbon atoms. There are exceptions to this, but I'm trying to teach you the general rules. Of course, as we showed in the previous slide, hydrogens that are stuck to sp3 hybridized carbons that are near more electron withdrawing groups will be further to the left and hence closer to 5 than analogous hydrogens that are not, which will be further downfield or closer to 1. Hydrogens that are stuck to sp2 hybridized carbons, that is double bonded CHs, appear from 4 to 6 ppm. Hydrogens that are stuck to aromatic carbon atoms, benzene ring hydrogens or other aromatic carbons, appear generally speaking about 6 to 8 ppm. Aldehyde hydrogens, generally speaking, appear right around 10. Phenol hydrogens sometimes appear at the same place, although I've seen them appear in other places, and they can vary depending upon the solvent and concentration at which the Proton NMR is run. Carboxylic acid hydrogens usually appear 12 to 14 ppm. Amide hydrogens sometimes appear 11 to 13 ppm, although once again I've seen a lot of variability there. Alcohol OHs appear 0.5 to 5.5 ppm, and amine NHs appear 0.5 to 5.5 ppm as well. Once again, in these last two, I've also seen a tremendous amount of variability depending on the concentration or the temperature or way in which the sample is run. Now let's see if I can describe that same thing in picture form. Once again, as I mentioned before, hydrogens that are stuck to sp3 hybridized carbons, generally speaking, will appear between 1 and 5 ppm. I personally like to call this single bond land, because we're talking about carbons that have all single bonds around them. The hydrogens stuck to those carbons appear, generally speaking, in this area. 4 to 6 is what I call double bond land, hydrogens that are stuck to carbons that are double bonded to other carbons. 6 to 8 are hydrogens that are stuck to benzene, or it could be other aromatic compounds. I call this aromatic land. Right around 10 we see phenols, that's this type of hydrogen, or aldehydes, this type of hydrogen shown in pink. 12 to 14 we see carboxylic acids and sometimes amides, although sometimes there's some variability here. And alcohol hydrogens and amine hydrogens generally show up in this range, 0.5 to 5.5 ppm, although there is sometimes a lot of variability there. And now I teach you one last thing about hydrogen NMR. Hydrogen atoms split the signal of neighboring hydrogen atoms. Now this might sound a little abstract, so here's an example. In this molecule, there are 3 hydrogens A and 2 hydrogens B. Now, because hydrogens A are next door to hydrogens B will be split by hydrogens A, and hydrogens A will be split by hydrogens B. I know you're probably thinking I'm insane and that sentence was really long, but let's consider an example to put all of this stuff together. So how do hydrogens A split the signals of hydrogens B and vice versa? I want you to remember the n+1 rule. Hydrogens A look next door and see 2 hydrogens B. You see that? The signal for hydrogen A then gets split as follows. 2 plus 1 equals 3. So the signal for hydrogens A will be a triplet. Similarly, hydrogens B look next door and see 3 hydrogens A. The signal for hydrogens B then will be 3 plus 1 is a quartet. You're welcome to repeat this slide if you want until you get this down. So now we're looking at this molecule, ethyl bromide. What can we say about its hydrogen NMR? Well, foremost, the signals of hydrogens B will appear further to the left or further downfield than the signal for hydrogens A, because hydrogens B are more positively charged since they're closer to the electron withdrawing bromine. Does that make sense? Now, regarding integration, we can see that hydrogens A still integrate for 3 and hydrogens B will integrate for 2. So here's the hydrogen NMR for this compound. Which signals belong to which hydrogens? Well, as expected, hydrogens B once again appear further downfield right here. You'll also notice that hydrogens B are a quartet. Why are they a quartet? Because they look next door and see 3 hydrogens A, and we add 1 to it. 4 means a quartet. Hydrogens A are further from this electron withdrawing bromine, so they'll appear further to the right or further upfield, right here. They are a triplet. Why? Because hydrogens A look next door and see hydrogens B, and there are 2 hydrogens B. I add 1 to it. That is a triplet. I hope that makes sense. So hydrogen NMR can be summarized as follows. 1. Each different kind or non-equivalent hydrogen gives a different signal. The more positively charged, the further to the left. 2. The heights of the integrals above each peak tell you the proportional number of hydrogens contributing to that peak. 3. Hydrogens get split by neighboring hydrogens. To figure out the splitting, count all of the hydrogens next door in all directions and add 1. Remember the following. Single bond land, 1 to 5 ppm. These are hydrogens stuck to sp3 hybridized carbons. Double bond land, 4 to 6 ppm. Hydrogens stuck to sp2 hybridized carbons, specifically carbons that are double bonded to other carbons. Aromatic land, hydrogens stuck to benzene or other aromatic rings. Right around 10, phenol and aldehyde hydrogens. 12 to 14, carboxylic acid hydrogens and sometimes amides. And 0.5 to 5.5 ppm, alcohols and amine hydrogens. Here are some examples to consider. I want you to predict what the proton NMR spectrum should look like for each of the following molecules. I'll let you pause now and do this before you go on, since the answers to these are shown on the following slides. Here are the answers to the first 2 examples. Here are the answers to the next 2 examples. And here is the answer to the last example. I'll leave it to you to see if you can understand what we've just seen. And as always, if you have questions, you can ask me in class. We now arrive at carbon NMR, which is frequently called C13 NMR. C13 NMR works almost exactly the same as hydrogen NMR with the following notable differences. First, carbon NMR gives signals for carbon atoms instead of hydrogen atoms. Second, instead of going from 1 to 14 ppm like hydrogen NMR, carbon NMR spectra usually go from 0 to about 220 ppm. Next, carbon NMR do not have integrals, and carbon NMR signals do not usually have splitting, because they're run in a way that decouples the splitting signals of adjacent atoms. So here's what you actually need to know about carbon NMR. 1. The trend remains true that more positively charged carbon atoms appear further to the left. 2. For carbonyl signals, I want you to remember the following. Carbonyl carbons in carboxylic acids, esters, and amides appear usually between 160 and 180 ppm. Carbonyl carbons in aldehydes and ketones appear usually about 200 or above. Now sometimes there's some slight wiggle room there, but that's generally speaking a pretty good trend to follow. So where do different carbonyl signals appear on carbon NMR? Well, remember that the carbon NMR spectrum goes from about 0 to 220 ppm. So as I said in the previous slide, I want you to remember carboxylic acids, amides, and esters. These kinds of carbons that are highlighted in pink generally appear about 160 to 180 ppm. There's some slight wiggle room sometimes, but not a whole heck of a lot. Generally speaking, aldehyde and ketone carbonyl carbons will appear about 200 or above. And once again, sometimes you see some wiggle room, but not a whole heck of a lot. This is extremely important. So I hope that you remember these things, because they will become relevant shortly. Here are some examples to consider. I want you to predict what the carbon NMR spectrum should look like for each of the following molecules. I'll let you pause right now and do this before going on, since the answers to this question is shown on the lecture slides that follow. Here is the answer for the first two examples. Once again, you can see, and I hasten to point this out, that this carbonyl carbon right here belongs to an ester. Notice where it shows up. It shows up between 160 and 180 ppm. Here are the answers to the next two examples. I hasten to point out once again, this carbonyl carbon is a carboxylic acid. Where does it show up? Between 160 and 180 ppm. Here's a carbonyl carbon to an amide. Where does it show up? Between 160 and 180 ppm. Here are our next two answers. I hasten to point out again, this carbonyl carbon is an aldehyde carbon. Where does it show up? Above 200. This is a carbonyl carbon for a ketone. Where does it show up? Above 200. I emphasize that for a reason that will become apparent shortly. And now we arrive at the final subject for this lecture, putting all of this crap together. How do we deduce a compound structure from spectral data? Here are my steps. Now I'm telling you, you don't have to do them in this order, but for me personally, I found this order to be the most useful way of being able to deduce a compound structure from spectrum. Step number 1, look at your IR for an OH and or a carbonyl. Step 2, if you have a carbonyl, as determined from the IR, then look at the C13 NMR to figure out where it shows up. If it shows up at 160 to 180 ppm, then your compound is an ester, amide, or carboxylic acid. If it shows up at 200 or above, then it's a ketone or an aldehyde. Now, if you don't have a carbonyl, so if you look at your IR and don't see a carbonyl anywhere, then you can pretty much ignore your carbon NMR, because it's not going to tell you anything useful, generally speaking, that you can't already figure out from the hydrogen NMR. Step 3, look at your hydrogen NMR for the following. First, look at your hydrogen NMR's integral height. Measure each of the sigmoidal curves above the peaks and determine their ratio. 1 to 2 to 2, or 2 to 3 to 3, or 4 to 2 to 2, or 4 to 2 to 3, or whatever that happens to be. Remember that those heights tell you proportionally how many hydrogens are in that peak. The next step is remember peak location. Based on where those signals appear, you can determine what kinds of hydrogens they are. Once again, if they're 1 to 5, single bond land. 4 to 6, double bond land. 6 to 8, aromatic land. 10, phenols or aldehydes. 12 to 15, carboxylic acids or amides. And anywhere kind of in this region would be the default for alcohols and amines. Step 4, put the pieces together that you've figured out from steps 1 through 3. Now, there may be multiple ways of putting them together. If so, then you use the splitting information to help figure out which way is correct. If there aren't multiple ways of putting those pieces together, then you really don't have to care about splitting, frankly. When you're all done, your proposed answer's mass should equal the one deduced from mass spectrometry data. Now, I should tell you, this step is the one that I personally like to call playing with Legos. You'll see why. So, let's do some examples. Let's say that I've got a compound who gives the following IR, C13, and HNMR data. Now, if I'm trying to deduce its structure, where do I begin? I, of course, begin with step 1. Step 1 from Mike's list of steps is look at the IR and try to figure out, does this compound have a carbonyl or an OH? Does it have a carbonyl? I see a huge peak at 1700. Heck yeah, it does. Does it have an OH? No, it does not. I know there's this little blip here, but that is way too tiny to be an OH for this type of compound. This is likely caused by a small contaminant, either an amine or water, that was in the sample when it was run by IR. Next step, I look at the carbon NMR. Because I have a carbonyl, I look at the carbon NMR to figure out where that carbonyl carbon shows up. Now you'll notice that this says offset 40 ppm right here. That means that this signal right here, which is the carbonyl carbon signal, is appearing 40 ppm to the left of about 160. So it's showing up above 200. So because this carbonyl carbon is showing up above 200, it has to belong to either an aldehyde or a ketone. This is the only thing that I do with my carbon NMR. And one thing I should point out is this. Carbonyl carbons will always be the carbons that appear furthest to the left on your carbon NMR. So don't start looking at signals anywhere in this region over here. Waste of time. The next thing that I do is I look at my hydrogen NMR and I do the integration. If I measure the height of this integral curve beginning at the horizontal line to horizontal line, so I start measuring it from where it goes horizontal to vertical and where it stops going vertical to horizontal. This height right here is the smallest of all of these integrals. I'm going to call it 1. Now if I measure this with my ruler, I've discovered that the height from here to here is around 5, proportionally speaking, with comparison to this integral over here. I've also discovered that the height over this peak from this horizontal to this horizontal is 2. And from this horizontal to this horizontal for this peak is also 2. So I've now done my integration. The next thing that I do with my hydrogen NMR is determine based on where these appear what they are. I've got a peak that's right close to 10 and it integrates for 1. What is that? It's of course an aldehyde. That's consistent with what I discovered in my carbon NMR. My carbonyl compound has to be either an aldehyde or a ketone. Now what about these signals? They appear between 6 and 8 ppm. What land is that? It's aromatic land. Now for these examples and the vast majority of examples you'll ever encounter on a standardized exam, the NMR spectra that you'll get for an aromatic compound will only be for a substituted benzene. That's it. So don't worry about other aromatics like pyridine or imidazole or some other crazy aromatic. We'll just stick to benzene. So how in the world can I get a benzene ring that only has 5 hydrogens on it? Well, of course it has to be a benzene ring that is monosubstituted. This is not a T-butyl group, by the way. This is just representing some substituent, I don't know what it is yet, dangling off of my benzene ring. I've got 1, 2, 3, 4, 5 hydrogens left, and they're all heaping up on top of each other in aromatic land. Now what about these? These signals down here appear all below 5 ppm. What land is that? It's single bond land. So if I have something that integrates for 2 and it's in single bond land, what could it be? It's a CH2. That's it. Here I've got another signal that integrates for 2, single bond land. What is it? It's a CH2. So what I've done right now is I figured out my pieces. I've got a benzene ring that has something hanging off of it. I've got a CH2, another kind of CH2, and an aldehyde. How in the world can I put those together? In other words, I'm at step 4. How in the world can I play Legos and put my pieces together? Well, first of all, I take my benzene ring, and if I look at the pieces I've got left, a CH2, another CH2, and an aldehyde, there's only one way I can consider putting those together. I have to have my one CH2, then my other CH2, then my aldehyde. Now that I've got my guess, I step back and look and ask myself, is this guess consistent with all the data that I have? My molecule has a carbonyl. Is there a carbonyl in the IR? Yes, there is. My molecule is an aldehyde. The carbonyl signal in the C13 NMR shows up above 200, which is consistent for an aldehyde carbon. Next thing, I look at my hydrogen NMR. This H right here should show up around 10. Does it? Yes, it does. It's right here. This benzene ring is 5 hydrogens in height, and it should show up somewhere in aromatic land between 6 and 8 ppm. It does right here. I've got a CH2 and another CH2, both of which show up somewhere in single bond land. Here they are. Is this compound consistent with all of my data? Yes, it is. So is it right? Oh, yeah. Let's do one more example. Let's say that I've got this IR and these NMR spectra. First thing I do is I look at my IR and try to figure out, is there a carbonyl? Is there one? Yes, there is. It's right here. Now, question is there an OH? Well, I don't see anything over here to the left of my CH stretches here. But what do I see? Well, I notice that these CHs get wide at the top. Do you see that? What does that wideness mean? Well, you might remember from our previous lecture that when it gets wide at the top, that tells me that there is an OH, and specifically that is a carboxylic acid OH. Now that I know I do have a carbonyl, I'm going to look at my carbon NMR and see where that appears. It's always the leftmost signal. The leftmost signal does indeed appear between 160 and 180, which tells me it has to be a carboxylic acid, an amide, or an ester. Now, once again, I can pretty well deduce from my IR that it is a carboxylic acid, so I don't really have to worry about amide or ester. Let's go on to our carbon or our hydrogen NMR. I'm going to do my integrals. The smallest integral I'm going to measure with my little ruler and decide, yeah, that looks like about 1 in height. I'm going to call however many millimeters that is 1. And proportionally, I'll measure from horizontal to horizontal each of the remaining integrals. Horizontal to horizontal is about twice that height, or twice the height of the integral over here, so this is 2. This one is also about the same, so it's 2. I also measure the remaining, and I find out 2 to 2 to 3. Now that I've measured my integrals, I figure out what those individual pieces are based on where they appear in the NMR. This signal over here is offset by 3.2 ppm, which means that it's actually appearing to the left about 3.2 ppm, so it's somewhere around 13. What kind of hydrogen appears at 13? Carboxylic acid hydrogen. What about these two signals? I've got signals that are 2 to 2 in 6 to 8 region. This is aromatic land. Now granted, this is slightly outside of 8. Don't worry about it. Aromatic land. How can I get 2 to 2 ratio in an aromatic land? What that is, it is a Paris disubstituted benzene. So these two hydrogens here, assuming that the substituents coming off opposite sides of the benzene are different, then the hydrogen coming off of here and here would be equivalent, and they would integrate for 2. The hydrogen here and here would also be equivalent to each other, but they'd be different from the other two, and they would also integrate for 2. You see nice, neat 2 doublets appearing in aromatic land. That tells you, bam, it is a para-disubstituted benzene. What about this? This is all appearing below 5, so it's all single bond land. 2 hydrogens, CH2. 2 hydrogens, another CH2. 3 hydrogens, CH3. I've now done everything I need to with these spectra. I just have to put the pieces together in my playing Lego step. The challenge with this particular molecule, or these pieces I should say, is that I could imagine 3 different ways of putting these pieces together. I got my benzene ring with my CH3 coming off of the left, my CH2, and my carboxylic acid coming off the right. That's one way I could put them together. Is there another way? Of course, I could imagine one of these CH2s being here and the other CH2 and CH3 coming off of the other side of the benzene ring. Or I could put all these pieces together in a third way. Benzene ring, carboxylic acid off the right, CH2, CH2, CH3 off the left. These are 3 different ways of putting these pieces together. One of them is correct and the other is not. How do I tell? By looking at splitting. Now in the previous example that we did, splitting was not necessary because there was only one way we could put the pieces together. When there are multiple potentially correct ways of putting them together, then you look at splitting. What would the splitting of the hydrogens here be? Well, these hydrogens look at the next door carbon and ask how many hydrogens are there. The answer is 0. So I take 0 and I add 1 to it. The hydrogens here would be a singlet. What would the splitting of these hydrogens be? Well, I look next door and I have 0 hydrogens here, and I look next door the other way. I've got 2 hydrogens there. I add 1 to it, he'd be a triplet. How about these hydrogens? I look next door and see 0 hydrogens on that carbon, 2 hydrogens on this carbon. I add 1 to it, triplet. Down here, these hydrogens look next door and see 2 hydrogens. I add 1 to it, triplet. These hydrogens right here look next door in one direction, see 0 hydrogens. Look next door the other directions, I see 3. I add 1 to it, they'd be a quartet. These hydrogens look next door and see 0 in this direction and 0 hydrogens in the other direction. I add 1 to it, they'd be a singlet. These hydrogens down here look next door and see 2 hydrogens. I add 1 to it, triplet. These hydrogens look next door in one direction and see 3. In the other direction, they see 2 more. I add 1 to that. It is a sextet. I wrote P for pentet, but that's incorrect. It should be a sextet, which is also called a sextet. These hydrogens look next door in one direction and see 0. They look next door in the other direction and see 2. I add 1 to it, they should be a triplet. Whew! So now that I've looked at the splitting patterns that each of these individual compounds would produce, I have to decide which of those is consistent with this NMR spectrum. Now, it might not be absolutely clear what the splitting pattern is here, but I'm telling you that if you were given an example on a standardized exam, they would make it much clearer. It's obvious, however, that none of these hydrogens signals is a singlet. This is obviously something wider than a singlet. This is something way wider than a singlet, and so is this. So any of these examples that have singlets in them, I can automatically eliminate. This CH3 is not a singlet. It looks like at least a triplet. This CH2 is not a singlet. Neither of these CH2s are singlets. So the only compound that would be consistent is this bottom one here. Now that we've guessed this answer, let's see if it's consistent with all of the data that I have. I look at my IR. I've seen a carbonyl and an OH consistent with a carboxylic acid. Does my guess have a carboxylic acid? Oh yeah. C13 NMR, the carbonyl shows up between 160 and 180, consistent with a carboxylic acid amide or ester. Is my guess one of those? Oh yeah. Based on my hydrogen NMR, I've got a signal that integrates for 1 somewhere around 13. That is consistent with a carboxylic acid OH. Do I have that in my guess? Yes, I do. I also have 2 separate signals, each doublets in aromatic land, integrating for 2 to 2. That is consistent with a di-substituted para-substituted benzene ring. Do I have that in my guess? Yes, I do. I also have, for my integration, 3 different signals in single bond land, 2 to 2 to 3, consistent of being a CH2, CH2, and CH3. The splitting tells me that none of these are singlets, so none of them can be isolated by itself as in these 2 guesses here. Thus, they must all be in a straight chain. Is my answer consistent with all of the data? Absolutely yes. Is my answer correct? Yes, it is. These examples have hopefully been helpful for you guys. I have additional examples posted on Canvas under our 2310 folder that you can look up our sample NMR packet. And this ends all of my lecture today on NMR spectroscopy. I hope that it's been helpful. Of course, the best way for you to learn it is to do it yourself, so I will give you several examples in our practice packet in class. Until then, have a good day.